Okay, this video is for Math 1, and we're in Unit 2.1.1. And what we're looking at is just being able to graph from both linear and exponential functions. So in this video, we're looking at just a linear case, but can we take a problem, write an equation, write a function of it, and then be able to graph that data, okay? So I have two examples here that I'm going to go through just to kind of show you the process that we want to be able to do. This one here says the Russell family is driving 1,000 miles to the beach vacation. They're driving at an average rate of 60 miles per hour. So there's write an equation that represents the distance remaining in miles. So that's the key right there. We want an equation that distance remaining, not how far they're going, but the kids are always asking, how much longer do we have to go? And time in hours they have been driving until they reach the beach. So again, this is in hours. It's our unit. We're going in miles. They plan on stopping 4 times during a trip. Draw a graph that represents all possible distances and times they could stop on their drive. Okay, so a couple things that we have to be conscious of. Okay, so the first thing we're going to do is write a equation or function for this. Okay, so let's I like to use variables that make sense. So I'm going to say d is the distance remaining. So I'm going to first define the variables. Distance remaining. Sorry, my pen's kind of sleeping there. And then t is the time in hours of actual driving. Now, the reason why we're making this graph is to be able to determine, okay, if we want to stop 4 times, how far can we travel? If you're looking at a map, say, okay, this city is like, 400 miles away. What time can it happen? So you're kind of mapping out your plan. So this is a chart to give you like data to look at. Time in hours. Okay. So the equation I'm going to come up with is the distance remaining. Now, when you start off, you have 1,000 miles to start off with. From there, your remaining distance decreases because you're getting closer to your end target. And it's getting closer by a rate of 60 miles per hour, okay? And there's your rate. So again, the rate, when I look at it, is 60 miles per 1 hour, and then we're multiplying it by t, which is in hours. So notice that's why the rate works out and we have miles left over. So even though we put down a single number, that's our slope, rate of change, it really is 2 units, 60 compared to 1. Now when we look at a graph here, what we have is a couple values. And this is going to be time, and this is going to be distance remaining. So the first thing I say is I'm going to start at 1,000. So 1,000's up here, and then 0's down here. Okay, and then 500's here. Again, I like to sketch these just so I can get a idea of what's going on. I think it's a good way to understand the problem. And when we talk about sketching, we say, okay, my first point is right here. Okay. Now let's say that we want to figure out how long it's going to take to get there. What we could do is take this equation, put 0 in for d. Let's say the distance is 0 miles left to go. And if we want to solve that, we could do this. Okay. And move the 60 over, add 60 to both sides. I guess it's something we quite don't get into yet, but I'm just going to show you a couple bonus things here. So if we add that to that side, we have 60t equals 1,000. And pen's a little slow getting there. Okay. And then we divide 1,000 by 60. So I use that on my calculator, and it takes us 16 2/3 hours for this to happen. Okay. So in time here, if again, I just do this as a bear, so let's do like 10 hours, and then 20 hours, and then 15 and 5. So at 16.7, so right about here-ish, we get to our destination. There's where we start. So the equation is really a linear process from here to here. Now notice, we don't put arrows on this equation because it doesn't continue. Once you hit your destination, you're done. And you start at 1,000 miles. So we don't add to the line. So this is like a line segment that starts and stops, and that is the whole part of the graph. So in this case, when we talk about domain and range, which we get to, we'd say, okay, our domain only lasts for 0 to 16.7 hours. This is all the time that it takes. And 1,000, from 0 to 1,000 is your range. That's all the distance that's calculated. Okay. So if we want to say, okay, after 5 hours, how far have we gone? We can go over to 5, you know, look up the graph, and then right there, roughly 7,500, 750 miles-ish, okay? Now another thing we could do is, I'm going to erase this work over here. Another thing we could do is get a list of data. So again, you can use this on the calculator, and that's highly preferred as well, to know how to use your calculator to get this. I want to make a little chart of these values. So we have the hours, okay, so that's my independent variable. And then my dependent variable is your distance, okay, left. So when we start off, we have 1,000 miles to go. Now again, we plug them in. So we know it's going to take 6.5, so I'm going to put 5 and 10, 10, and then 15. And then we already know that 16.7-ish, we end up at 0, okay? So if I take 5 and plug it in, we literally, this is how you would do it. 1,000 minus 60 times 5. So again, we could plug that into our calculator. Sorry, my pen's a little slow there. So we have 1,000 minus 60 times 5 is 700. So after 5 hours, we have 700 miles to go. And then we do the same for the other values. Just plug in 10 in for t. So we're evaluating that. And we have 400 miles left, so that's pretty good. Not 4,000, how about 400? Let me erase that. And now we're down to 15. So we have 1,000 minus 60 times 15 hours. Notice we have just 100 miles left. So we can kind of see the data here. So I'm going to say, okay, after 15 hours of driving, we're almost there. Is there a town close by that we could stop, get some more food, whatever the case is. So again, a way to write equation to get that, so just so you're not guessing. So that's kind of what we're looking at here for this one. Now this next example, I'm not going to go through the whole problem, but I just want to kind of get you started here. And here we have a scenario where we have a function, which is how much money you make, but it's based on two separate equations working together. So it says Jake graduated high school, is working for a family furniture store to save for college. He earns $12.50 per hour plus commission. Okay, so I'm going to say E for how much he earns. Okay, and that's how much money he's going to make. And it's based on hourly, so I'm going to put, again, T for the time in hours. And then I'm going to also put on, I'm going to say S for the how much he actually sells. Okay, so those are the things that we're looking at here as well. Okay, so the first equation is he earns, E, is equal to $12.50 per hour of work. Okay, and again, the 12.50, if I write it as a rate of change, is $12.50. So that's money over 1 hour of time. So there's my two labels. You always want to compare your labels there. Okay, so that's the first equation. Now the second equation is commission. So it says after he sells $500, then he makes 15% of everything that's left. So notice they give you that function right here, where C is the amount of commission he makes, and X is how much he sells. So let's identify those variables over here. So X is how much he sells, and notice C is the commission on such thing. Sorry, my pen's running low there. My S's kind of disappeared there. Those should be S's. Okay, that's better. So that equation is 15% of something, of what? Now notice it's X minus 500 because the first $500 he does not get commission on. That goes to the store, so that kind of makes sense. So now when we evaluate something, we have to consider both items. We have to be able to evaluate how much time was put in, and then also how much he sold. And then this total tells you how much money he has earned. So again, that's just a little beginner on, you know, the points of this problem, and that'd be a good problem for you to handle on your own.